All right, so we started this stuff last time, this biaxial strain. Now, as I mentioned, it's an awful lot like biaxial stress. It's very similar in how the equations look and all that. Now, this does not, at least in my view, have the same importance as biaxial stress. So I'm not going to spend quite as much time on it. This will tell us how things deform at given angles. Now, generally, we're a little bit more concerned about whether things break or not, what the stresses are at different angles, than we are with the strains, okay? Strains deformation, which of course is important, but a lot of our focus is on stress, because that can lead to things actually failing, which is obviously bad. And there's kind of a little bit of a problem with this. This is on page 470. And you can see the problems on page 470 and 480 if I don't want to spend a lot of time on this. They're rather involved, okay, which is one reason I kind of wrote them out, okay? Those are the derivations. So this is a little bit like the biaxial stress derivations, and that wouldn't test you on the derivation itself. I just want you to kind of understand where it comes from, and then we want to be able to work with the results. So once again, I went over this kind of quickly on Friday, I know, and I'll just review it again. What we're looking at here is a little element with dx and dy, so one of those little calculus things. That's the dimensions of that little rectangle. We've drawn a line from corner to corner, opposite corners, that we're calling ds. That's at an angle theta. Now, one thing I'll mention here is that angle is not with the vertical this time. This reference angle is with the horizontal. And that's one difference between doing the stress and the strain, is the reference angle here is with the horizontal. What we want to do here is look at three different things we could do to that rectangle. We can stretch it out in the x direction, in which case the length of that stretching would be epsilon x times dx, the strain times the original length. We can stretch it out in the y direction, epsilon y dy, or we can cause some shear strain in it, gamma xy dy. And in each case, what we want to do is see what the effects are on this original diagonal line, how much longer it gets when we do those things, okay? As that corner point moves on account of these strains we're applying. And that will lengthen the diagonal line that goes across. So what we do, for instance, for the epsilon x dx is we plot up on the top our epsilon x dx, and then we realize that we can look at a little right triangle in here that will kind of approximate what's happening. It won't be perfect, but it'll kind of approximate it. So if we take that original line there and pull it over epsilon x dx, if we kind of create this little offset, we can approximate the deformation of that corner point with a right triangle. This angle theta will be pretty much equal to that angle theta. So that new extra length will be epsilon x dx cosine of theta to get that component on the triangle. Okay. And we do that basic process 3 times with the triangles that I'm showing here, and we add them all up and get the total delta on that diagonal line. Delta d total, as I call it. Okay. Then we're looking at a change in length there, but we want a strain, so we divide out the original length ds. And then we realize that dx over ds is cosine theta and dy over ds is sine theta. We change those values, come up with this formula, but that's a little awkward to work with, so we throw, I think they're called half angle formulas in there, and we come up with the final result. Okay, there it is. That's equation 71 from your formula sheet. That's the one we want to keep on the bottom. And what the deal is if we know the strains in the x and y directions, the normal and shear strains, we can calculate the strain at any direction we want, any angular direction. The one little thing that's, and now notice that looks an awful lot like the biaxial stress equation. With the one exception, there's a 2 here under the shear. And the other exception is we measure the angles now, not with the vertical reference, but with the horizontal reference. Okay. All right. Now the next page gets even a little bit messier, okay? 480. So are we good with what I just did there? the emphasis again, we're engineers, we'll use it. We're not going to derive it, we're going to use it. That's the idea. Okay. All right. Now the next page here, this is a little bit trickier, but it's the same sort of idea. You look at the effects of applying epsilon x dx, epsilon y dy, and gamma xy dy, and we look at the effects on this corner, but this time we look at how that line rotates based on applying those deformations. And we do it with triangles again, a little bit different triangle, but the idea is the same, and we come up with the rotation angle 3 times. These would be angles in radians. So I call them alpha prime, prime, and alpha prime, prime, prime. We add them up. And then again, we use dx over ds as cosine theta, dy over ds as sine theta. We do some substitutions, and we come up with a formula that will tell us how that diagonal line from one corner to the opposite corner would rotate after you apply an epsilon x, an epsilon y, and a gamma xy. And we come up with this formula right here for alpha. That's the rotation of a line, as it is affected by epsilon x, epsilon y, and gamma xy right there. And that's the equation for the angle we call alpha. That's equation 77 on your formula sheet. So that will tell us how a line rotates. Now the shear strain, though, is a change in an angle, which is the rotation of both sides of the angle. So it's the rotation of 2 lines. The angles are commonly called alpha and beta. So if we have some right angle element kind of cutting its way across here, and we want to know what's the shear strain going to be down here, we got to look at the rotation of 2 lines to get that figured out. We just found the formula for alpha. To find the formula for the other line, we add 90 degrees to all of these thetas in here, because the alpha beta is at 90 degrees to alpha. They're 90 degrees apart. Do a bunch of trig identities, add everything up, and add it together, add alpha plus beta, and we'll get gamma, that formula for gamma x1, y1. And that is formula 72. And that's the shear strain formula. It lacks a 2 right there that you would find in the stress formula. I think that's what's in the stress formula. No, it's not. I'm sorry, the 2's over here in the stress formula. So it's a little bit different than the shear stress formula in that it lacks that 2. All right? And that's probably about the extent to which I'll derive those. Okay? Hopefully that'll be okay. So we got kind of the rules on 490 that summarize some of this. We've got 3 formulas that we use. The epsilon x1 formula, which is formula 71. We've got the gamma x1, y1 formula, which is formula 72. Okay, so this tells us how an angled line would lengthen or shorten based on knowing the strains in the x and y directions. This tells us how an angle would change, similar to what you're seeing there, given strains in the x and y directions. And this alpha formula tells us how one line would rotate right there. Okay. That's the information we can get out of those. Now this is biaxial, okay? So just like biaxial stress, we've got principal strains this time. And if you look at those formulas for calculating them, they're quite similar to the biaxial stress formulas. Okay? And the principles, the ideas are the same. You've got a formula to find the angle at which one of the principal strains acts. The other one will be 90 degrees apart from it. The shear strain at that angle will be 0. The maximum shear strain will be 45 degrees off of the principal normal strains. Okay. The normal strain at that angle will be the average normal strain. Okay. So why don't we look at an example of this, because I think this is best covered by example, I think. So why don't we do that? This is 5:30. I'm skipping ahead a bit. let's say we've got a plate as shown, and we have measured the strains in the X and Y directions, and the strained position of that plate is shown with the dashed lines. So what we're doing is we're lengthening it in the X direction by 300 times 10 to the minus 6. It's common for these strains to be quite small, so the symbol for 10 to the minus 6 is the Greek letter micro. That's often used. So epsilon x will be positive 300 times 10 to the minus 6. Okay. If you look at those dashed lines, you'll notice in the y direction, the plate's getting shorter by 512 times 10 to the minus 6. So that's negative 512 micron. And then you'll notice that that right angle in the lower left-hand corner, that's our reference angle, is getting smaller by 210 times 10 to the minus 6. That would refer to radians. Okay? It's getting smaller, which if you remember from what we did Wednesday, I think it was, is a positive shear strain. So that's positive 210 times 10 to the minus 6. So those are the given strains in the X and Y directions from the picture there. The little derivation there for the angular relationships are on page 410 if you ever want to look at them. If the lower left-hand angle gets smaller, it's positive shear strain. If the lower left-hand angle gets bigger, it's negative shear strain. Okay. Now what we want to know in this particular example is if we have a square that was etched or drawn on that plate at 30 degrees with the horizontal, what's it going to look like after, and this is before the plate is deformed at all. What will that square look like after we deform it, okay, after we deform the plate? Now notice you're not given how it deforms at 30 degrees, you're given how it deforms in the X and Y directions. So that's what we use the equations for, is to figure out how it would deform at 30 degrees. So our first angle for epsilon x1 is 30 degrees because the horizontal plane is the reference angle. And then the other, for epsilon y1, we just add 90 to that and we get 120 degrees. So those are our two angles. So that's the given information there. Okay. All right. And from there, you plug into the formula. That's about it, okay? So once you kind of understand what you're doing here, you just plug the stuff in. So epsilon x is 300, epsilon y is 512, negative. So epsilon x plus epsilon y over 2 is 300 minus 512 over 2, then plus epsilon x minus epsilon y, so that's 300 minus a negative 512 over 2. Cosine of 2 theta is cosine 60, plus gamma xy over 2, 210 over 2 times sine of 60. Run the numbers and you get the strain in the x1 direction at 30 degrees. It's 188, and that micro again means times 10 to the minus 6. So we just plug in the micro at the end. I don't bother carrying it through because that equation is messy enough, and it gets really messy if I carry it through. All right, so that's the strain at 30 degrees. I can do the whole process over again, this time for 120 degrees, double it, I get 240. Plug in everything, and I get to the strain at 120 degrees. It's negative 400. Okay. Again, it's just plugging into the formula. I'm using formula 71 to find the normal strains in that plate. right. Now, just like there's a shortcut formula for the stress biaxial, there's a shortcut formula for the strain. It's right there at the bottom. I can go ahead and plug into that. Epsilon x plus epsilon y, which is 300 minus 512, is epsilon x1, 188, plus epsilon y1. I can solve for epsilon y1, it's negative 400. Just a shortcut formula. Okay. We're good with that? Doing right? Okay, the last little bit is the shear strain. And again, it's just plugging into a formula. That's really all it is. Epsilon y minus epsilon x times sine 2 theta plus gamma xy cosine 2 theta. So that's negative 598 times 10 to the minus 6. Now, we might ask, well, what does this mean, okay? And that's what that little sketch down at the bottom is for, so we kind of understand the repercussions of this. What we've got the strains in the x and y directions. What we want to do is find the strain on that element at 30 degrees. We just found what they are, so now we can sketch up a schematic of what they look like. Now, by a schematic, I mean this isn't going to be a perfect picture. It's going to tell us the idea of what that thing looks like, that we can dimension. Okay, so that's the last thing we do is on that sketch. So I know that epsilon x1 at 30 is 188 positive, epsilon y1 which at 30, which is epsilon x1 at 120, same thing, negative 400, and gamma x1 y1 at 30 is negative 598. So if I'm going to sketch that up, it's going to look something like that. It's going to lengthen at the 30-degree angle by 188 times 10 to the minus 6. It's going to shorten in the y direction because it's negative 400 times 10 to the minus 6. And then that lower left-hand angle will get bigger by 598 times 10 to the minus 6 radians. Okay. Now that's kind of a schematic. It's drawn that way so you can dimension it. And when you're doing these sketches, kind of the idea to remember on this is you've got to declare a reference point. Our reference point is the lower left-hand corner. And in addition, so that we can create one nice dimension for the angle, we also create a reference line. So this isn't an entirely realistic sketch because we're holding that lower line to be a reference line. That line would actually rotate down a little bit if that angle got bigger. But just so we can dimension it nice and clean on one side, we hold that steady and show all the angle on the other side. So that's a bit of a schematic, but it gets you the idea of what would happen to that square after these strains occurred. Okay. Yeah?
So on the right bottom there's 188 micro and it lengthens it.
Right. Yeah.
On the top it's 400.
Right.
But it shortens.
Right. Okay. I think that there's a thing, and I'm just running out of time, but I'll get to it. But in the strain, the reference plane is the horizontal plane. It's different than stress. So the 30-degree direction is right here. And when we say this is 188, we mean the line at 30 degrees with the horizontal lengthens. It's the conventions are a little different than the stress, which is why that might be a little weird how it looks. Okay. Similarly, 90 degrees off of that, this shortens up. It's a little different in the directionality of it, I guess. Okay. And we'll get to that later. All right. Okay, I'll get you one more of these and then I'll run with this stuff. 231, I think. Yeah, 231. We'll try and make that due Friday. We'll see how that goes, but we'll look at 231. We'll have that due Friday too. That's the 8th. Okay. All right. So we got our test on Wednesday. Usually I give a little extra time for that, so an hour, 15 minutes or so, because with all that biaxial stuff, it takes time to knock through it. So it'll be a little bit more than an hour. Then we'll take a break, and then we'll cover these homework problems that are coming due after that. That'll be the plan. Okay. All right. So that'll be Wednesday. You know, if you got questions, come by the office, or you can email me too. If you know, maybe attach a PDF of a sketch or something if you got a question on something. That's always helpful. Okay, and I'll keep an eye on that and try and get back to those. All right.